You know, in physics, sometimes the most useful tools are the ones we kind of take for granted. These clever shortcuts that make absolutely impossible math, well, possible. But what if one of those super important shortcuts was built on an idea that wasn't really truly proven? Well, that's exactly the question we're going to dig into today.
So, it all kicks off with what sounds like a simple question. What happens when you fire a really powerful laser at just one single atom? Now, this isn't just some abstract thought experiment. This is the real deal basis for understanding pretty much everything from how lasers work to medical imaging. And it turns out, predicting that little dance between light and matter, it's one of the biggest challenges in all of quantum physics. All right, so to really get a grip on this, let's start by looking at the interaction itself.
Okay, so what we're really trying to do here is figure out the rules for how the laser's field, which is constantly changing, messes with an electron inside an atom. I mean, remember, light is an electromagnetic wave, and the electron has a negative charge, so you can imagine it gets kind of pushed and pulled all over the place by that wave. Now, tracking this perfectly is a huge deal, but the full nitty-gritty math is just unbelievably complex. So physicists did what they do best. They came up with a really smart way to simplify things. And this is where we get to see the genius of scientific modeling in action. When a problem is just way too hard, you find a smart assumption that makes it solvable.
And that shortcut is called the dipole approximation. The core idea is actually pretty simple. Instead of doing the insane calculation for the laser's effect at every single point across the tiny atom, you just pretend the field is constant. You take the value of the field right at the atom center, at the nucleus, and just apply that to the whole thing.
Now, the reason they can get away with this is pretty fascinating. Why does this work? It's all about scale. An atom is just ridiculously tiny. We're talking about a tenth of a nanometer. But the wavelength of the light hitting it, that's hundreds of nanometers, literally thousands of times larger. The field just doesn't have a chance to change much over that teeny tiny distance. Here's a great way to think about it. Imagine you're a single grain of sand on a beach, and a massive ocean wave is rolling in. For you, that tiny grain, the surface of that huge wave would seem practically flat. You're just too small to even notice the curve. It's the exact same idea here. The atom's electron only sees a tiny, uniform little slice of that much, much bigger light wave. Seems perfectly reasonable, right? But here's the thing. In science, and especially in physics, seems reasonable just doesn't cut it. And this is where our investigation really begins. It's time to put this assumption on trial. So here's the real kicker. For decades, this whole approximation was justified by what's called a heuristic argument. That's basically a fancy way of saying, hey, it seems reasonable, it feels right, and it works in practice. It's like a really good rule of thumb. But the big lurking question was there a rock-solid formal mathematical proof that it was legit, or was it just a convenient trick we'd all been using?
I mean, this raises a pretty wild question. Could it be that for years and years, countless calculations, predictions, and even whole experiments were based on a shortcut that, while super useful, wasn't actually rigorously proven? Were we all just getting lucky? And that's where a 2016 master's thesis by Leah Boseman comes in. It basically set out to put this whole assumption on trial. The goals were super clear and ambitious. First, take that seems reasonable argument and make it mathematically bulletproof. Second, prove the shortcut works perfectly in the most extreme case, when the laser's wavelength gets infinitely long. And finally, figure out exactly how much error this shortcut actually introduces. So, after pages and pages of intense mathematical gymnastics, what was the result? The verdict on this long-held physics shortcut was finally in.
Yup, proven. The dipole approximation is mathematically sound. That old heuristic argument, it holds up. Physicists weren't just getting lucky after all. Their physical intuition was totally spot on. And the thesis itself says it all, loud and clear. It confirms that the simplified model perfectly lines up with the exact, much more complex reality under exactly the conditions everyone always assumed it would. This is a huge validation for a tool that gets used all across physics. And listen, this was no walk in the park. This wasn't some simple proof. This required a super deep dive into some heavy-duty math, using powerful machinery like Cato's and Euclide's theorems. These are the kinds of tools you need to wrestle with the evolution of complex quantum systems over time. Okay, so we know the shortcut is valid. Awesome. But that's really only half the story. The next big question is, how good is it in the real world? What's the fine print?
The thesis didn't just stop at a simple yes, it went on to actually quantify the error. This is something called the rate of convergence. In other words, how quickly does the approximation get better, and how does it behave over time? Just how accurate is it?
And the analysis turned up two absolutely crucial relationships. First, just like you'd guess, as the wavelength of the light gets longer, the error gets smaller. The flatter the wave looks to the atom, the better the approximation. But, and this is key, the longer the laser interacts with the atom, the bigger the error grows. The shortcut actually gets worse over time. And they even put a number on it. The error shrinks in direct proportion to the wavelength, which is fantastic news. But it also grows over time, proportional to time raised to the power of 5/2. Now, what this does is give physicists a concrete formula, a rulebook for understanding the exact boundaries of one of their favorite shortcuts. So why does all this matter? Well, this work does so much more than just check a box. It puts a real number on our confidence in a fundamental tool. It tells scientists precisely when they can rely on this approximation, whether they're designing new lasers or modeling what's happening inside a star. And more than anything, it's just a beautiful example of scientific rigor, of the hard, detailed work it takes to make sure our foundations are solid as a rock. And that leaves us with a really fascinating thought to end on. This entire journey was about proving something that everyone, for the most part, already felt was true. It kind of makes you wonder, doesn't it? What other intuitive assumptions, what other clever little shortcuts in science are still out there, just waiting for their day in court?